Hello everyone and welcome to the course of Local Computer Network. This course is more than just theory, it's about building real understanding and confidence. In this video, we'll explore key concepts in data transmission, local network, Ethernet network, the TCP/IP protocol, and wireless local area networks. Let's dive into the world of modern networking. Ethernet network forms the foundation of local area networks LANs. Today's LAN market is defined by an unprecedented level of standardization around Ethernet. Ethernet has evolved over time with several types: thick Ethernet or 10x5 and thin Ethernet or 10x2 use of coaxial cables. 10 broad 36 support broadband signals over longer distance. 10x2 runs over twisted pair cables, while 10x F uses fiber optics. Fast Ethernet like 100x T and 100x F increases speed to 100 megabits per second. Gigabit Ethernet or 1000 by T offers even faster transmission. And finally, wireless Ethernet provides flexible cable-free connectivity. An Ethernet frame begins with a preamble, a sequence that helps devices synchronize. Next comes the start frame delimiter, which marks the beginning of the actual frame. Then the destination address identifies the receiver, and the source address shows who sent the frame. The length or type field tells us either the size of the data or the protocol used. After that comes the data itself, the message being sent. Finally, the FCS, also called CSE, checks the errors to ensure data integrity. MAC addressing defines how data is delivered on a network. In unicast, data is sent to a single specific device. Multicast sends data to a group of devices that are interested in the same content. And broadcast sends data to all devices on the local network. Each method serves a different purpose in efficient data communication. CSMA with CGR carrier sends multiple access with collision detection. Devices listen before sending data. If two devices transmit at the same time, a collision occurs. A jamming signal is sent and each device waits a random time before trying again. The TCP/IP protocol. TCP ensures reliable delivery of data by breaking it into packets and checking for errors. IP handles addressing and routing, making sure each packet reaches the correct destination. The TCP/IP model has four main layers. The application layer interacts with software and user services like web browsing or email. The transport layer ensures reliable data delivery using protocols like TCP or UDP. The network layer handles routing and addressing mainly through IP. Finally, the data link layer manages how data is physically sent over cables or wireless links within the local network. The application layer provides services directly to users and applications. For example, HTTP is used to browse websites, FTP is used to transfer files between computers, and SMTP is the protocol used to send emails. These protocols make communication over the internet simple and user-friendly. The transport layer is responsible for delivering data between devices. TCP provides reliable communication by checking for errors and ensuring all data arrives in order. UDP, on the other hand, is faster but less reliable. It's used for real-time services like video calls and online gaming, where speed matters more than perfection. The network layer is responsible for moving data between networks. It uses IP addressing to identify each device and routing to choose the best path for data to travel across the internet. Routers read IP addresses in each packet to deliver them to the correct destination even across different networks. The data link layer controls how data is sent over the physical network. It's responsible for framing, MAC addressing, and error detection within the same local network. This layer ensures that data moves safely from one device to another over cables or wireless signals, like through Ethernet or Wi-Fi. IPv4 and IPv6 are both addressing systems used to identify devices on a network. IPv4 uses 32-bit addresses written as four numbers separated by dots, like 192.168.1.1, but with a growing number of devices. IPv6 was introduced. It uses 128-bit addresses, allowing for many more unique IP. IPv6 addresses look like long strings of hexadecimal numbers. Migration from IPv4 to IPv6 is necessary to support the future of the Internet, and it's done using techniques like dual stack, tunneling, and translation. Anyway, we will explain this later. You can find your IP address by pressing Windows plus R, then type cmd, then write ipconfig. You will get your own IP. IPv4 structure. Each octet is 8 bits, making up a total of 4 bytes. For example, this IP address is represented in binary, allowing computers to locate and communicate with each other across the network. IPv6 structure. This address is written as 8 groups of 4 hexadecimal digits called hexstacks. Each group is separated by colons, like in this example. IPv6 was designed to overcome the address limitations of IPv4 and support future Internet growth. In the topic Migration from IPv4 to IPv6, we will explain this in detail, strategies and steps. Let's start by strategies. To migrate, one strategy is dual stack, where both protocols run on the same system during transition. This ensures compatibility and smooth communication. Tunneling is a migration technique that allows IPv6 packets to travel through an IPv4 network by encapsulating them like regular IPv4 traffic. It's useful for connecting IPv6 networks, but it adds complexity and might cause some delay. NAT protocol translation or NAT bridges the gap between IPv4 and IPv6 by converting packets between the two. It allows phased migration and cross-protocol communication, but may impact performance and isn't ideal for every application. Now we move on to explaining the steps. Start by assessing your network. Identify all devices and services currently in use. Then choose the appropriate IPv6 transition strategy, whether it's dual stack, tunneling, or NAT64, based on your specific infrastructure and future goals. Next, develop a transition strategy. Set a realistic timeline and budget based on your network's complexity. A phased approach is recommended. Begin with public services like websites and email, then gradually move to internal systems. Once migration begins, thoroughly test IPv6 connectivity and monitor performance. Check that all applications function properly with IPv6 and make sure your security settings are correctly configured. IPv4 addresses are divided into 5 classes. A, B, and C are commonly used for networks. Class A supports large networks with millions of hosts. Class B fits medium-sized networks, and Class C is for small networks. Class D and E are reserved for multicast and experimental use. A network mask or subnet mask separates an IP address into two parts: the net ID, which identifies the network, and the host ID, which identifies individual devices on that network. Subnetting divides a large network into smaller, manageable subnetworks or subnets. This improves security and efficiency. CIDR or classless interdomain routing uses flexible subnet masks like 24 or 26 instead of fixed classes, allowing better use of IP addresses. The ping command checks connectivity between your device and another on the network, showing response time. Tracers on Windows or Traceroute on Linux shows the path that packets take across the network, helping diagnose where delay or failure occurs. Local computer networks are the backbone of modern communication and data sharing. We invite our students to explore and engage with this exciting field. Your future in technology starts here.